Imagine you are holding a rope. You can feel the texture of the fibers against your skin, the slight give and take as you adjust your grip. You can feel it in your hand. You pull it tight, and the rope becomes taut, resisting your pull with an equal force. This feeling, this pull, is tension force. It's the force that acts along the length of a stretched, flexible connector, such as a rope or cable. Tension force is a force that exists within a material that is being stretched or pulled. It acts to restore the material to its original length. We encounter this force every day, whether it's in a game of tug of war, climbing a mountain, or simply hanging clothes to dry. Tension is at work. It's a fundamental concept in physics. Understanding tension helps us grasp how forces interact in various systems. Understanding tension is crucial for understanding how many things work. It helps us design and analyze structures and mechanisms. From simple pulleys to complex suspension bridges, tension plays a vital role. It ensures stability and functionality in engineering and construction. In this essay, we will explore the concept of tension force. We will delve into its principles and applications. We will look at its definition, examples, and how it is calculated. By the end, you'll have a comprehensive understanding of tension force and its significance. Tension is a force that is transmitted through a rope, string, cable, or any other object that can be pulled taut. When you pull on a rope, the force you apply is transmitted along the length of the rope. This transmitted force is the tension force. It always acts along the length of the material and away from the object applying the force. Tension force is a contact force, meaning it requires physical contact between objects. It is also a pulling force, not a pushing force. We encounter tension force in numerous everyday situations. One common example is hanging a picture frame. The weight of the frame pulls down on the string, creating tension in the string. This tension force prevents the frame from falling. Another example is a game of tug of war. Each team pulls on the rope, creating tension within it. The team that exerts a greater force creates more tension, ultimately pulling the rope in their direction. Section 4. Tension in free body diagrams. Free body diagrams are essential tools in physics for visualizing forces acting on an object. These diagrams help us break down complex physical situations into simpler, more manageable parts. By isolating an object and representing it with a dot, we can focus on the forces acting upon it without getting distracted by other details. In a free body diagram, an object is represented as a dot. This dot serves as a simplified model of the object, allowing us to concentrate on the forces at play. The forces acting on the object are represented as arrows. Each arrow points in the direction of the force it represents and is drawn to scale to indicate the magnitude of the force. The direction of the arrow indicates the direction of the force. For instance, if a force is pushing or pulling to the right, the arrow will point to the right. When tension is involved, it is represented by an arrow pointing away from the object along the line of the rope or cable. Tension forces are always directed along the length of the rope or cable and away from the object. For example, in the case of a hanging object, the tension force arrow points upwards, opposing the downward force of gravity. This balance of forces is what keeps the object stationary or moving at a constant velocity. Understanding how to represent tension in free body diagrams is crucial for solving many physics problems. Section 5. Tension on inclined planes. Tension becomes more complex when we introduce inclined planes. Imagine a block on a ramp attached to a rope that goes over a pulley. The weight of the block pulls on the rope. This creates tension in the rope. The tension force now has two components, one parallel to the ramp and one perpendicular to the ramp. The component parallel to the ramp opposes the component of gravity that wants to pull the block down the ramp. Section 6. Calculating tension formulas and equations. To calculate tension, we use Newton's second law of motion, which states that force equals mass times acceleration. F equals ma. This fundamental principle is the cornerstone of classical mechanics and helps us understand how objects behave under various forces. By applying this law, we can determine the tension in a rope or cable when it is subjected to different forces. When an object is at rest or moving at a constant velocity, the net force acting on it is zero. This is known as equilibrium. In such cases, all the forces acting on the object balance each other out. For instance, if a book is lying on a table, The gravitational force pulling it down is balanced by the normal force pushing it up. In a simple scenario with a hanging object, the tension force, T, is equal to the weight of the object, mg, where m is mass and g is the acceleration due to gravity. This means that if you know the mass of the object and the value of gravitational acceleration, you can easily calculate the tension in the rope or cable holding the object. In more complex situations like the inclined plane, we need to consider the angles and components of the forces involved. The tension in the rope or cable will depend not only on the weight of the object, but also on the angle of the incline and the frictional forces at play. By breaking down the forces into their components, we can solve for the tension more accurately. Section 7. Conclusion: Tension in the real world. Understanding tension force is crucial in many real-world applications. Engineers rely on it to design bridges, elevators, and cranes. Without a proper understanding of tension, these structures would be unsafe. Tension is also vital in fields like sports science, where understanding the tension in muscles and tendons is crucial for analyzing athletic performance. From the simple act of tying a knot to the complex engineering of skyscrapers, tension force is a fundamental concept that governs our physical world.